Welcome to the video. My name is Jack, and I hope you're having a wonderful day. Together, we're going to be learning about how to create an escrow program in Solana. You've learned the basics of Solana, and you've gotten a first taste by creating a simple Hello World program. Now you're ready to dive into your first major piece of Solana code. Let's get started. So, what exactly is an escrow program? Suppose that Alice has 100 Apple coins that she can redeem one-to-one for apples, and Bob has 100 banana coins that he can similarly redeem for bananas. However, they both want to eat a more balanced diet. How could they fairly and securely swap with each other without meeting up? In traditional finance, you need a trusted third party. Alice tells the bank that she wants to swap 10 Apple coin for 20 banana coin and deposits her 10 coins. Bob comes along and sees that this is a fair deal, so he deposits his 20 banana coins. The bank makes a swap and probably collects some fees from both for acting as the middleman. Can we do this more quickly, safely, and cheaply with DeFi? I think we can. On Solana, we can create a program that acts as a trusted intermediary. By publishing the code as a program on chain, we can allow anyone to create and fulfill these kinds of swaps in seconds for any pair of tokens. Anyone can inspect the code to make sure that it's safe and fair and fees are minimal. This kind of program is what we're going to be covering today. Why is it important to study this escrow program? In this program, you're going to learn the basic functionality to make on-chain functions that handle instructions coming in, invoke other programs on the blockchain, control who can interact with your functionality, store data, store tokens, transfer tokens between different wallets. These are all important basic building blocks of working with Solana. Understanding these primitives will enable you to understand a large majority of the on-chain programs on Solana. This escrow pattern you're about to learn is a foundation for all the applications you see here and much more. Let's get a bit more technical into how our escrow program actually works. Alice is going to interact with the escrow by telling it that she wants to create a new escrow to swap 10 Apple coins for 20 banana coins. The escrow program will then create a new escrow for Alice. This escrow is a PDA owned by the escrow program. It will also create a new vault account to store Alice's 10 Apple coins. This vault is also a PDA, but since it's an account to store tokens, it's owned by the token program. Its authority, who is authorized to remove tokens from it, is the escrow that Alice created. Suppose that Bob comes along and sees this escrow and thinks it's a good deal. He then sends an instruction to take the escrow along with 20 banana coins. The escrow program then closes out both the vault and Alice's escrow and distributes 20 banana coin to Alice and 10 Apple coin to Bob. Alternatively, suppose that before anyone comes along, Alice changes her mind. She can send an instruction to refund the escrow. This also closes out both the vault and the escrow. Then it refunds 10 Apple coin back to Alice. Alright, so now that we have the background, let's get into the code. First, we're going to give an overview of the file structure and the architecture of the program. Let's open up the project in our code editor, and we're going to focus on the Rust code inside this program's anchor-escrow folder here. So, inside the source folder, we have this lib.rs file, which is the entry point to any anchor program containing the main logic. There's several other helper files that lib.rs is importing and using. State.rs defines the main escrow data structure that we're creating. Inside the context folder, make, refund, and take respectively define the logic to make an escrow, refund an escrow, and take an escrow. Let's also check out this mod.rs file here. This file makes Rust recognize this whole context folder as a module. It imports each of make, refund, and take into itself, and it publicly exports all of them. This lets our lib.rs file just import the context module rather than importing all three of these individually. Let's also briefly touch on the cargo.toml file, which defines the dependencies that the project needs. If you're starting this project from scratch, you'll need to make a few changes to this file. So anchor-SPL is the anchor tooling that our program needs to talk to various standard on-chain programs. So in our case, we need to add it because we're talking to various token programs. So at the bottom, we add this dependency anchor-SPL equals 0.31.1. We also add anchor-SPL IDL build to IDL build here. The IDL is a JSON file that serves as your program's public interface so people can know how to interact with it. This line will let the IDL generation support tokens. Finally, we add this line features init if needed to anchor-lang. This enables a feature that creates accounts if they don't already exist. In the swap, we may need to make a banana coin account for Alice or an Apple coin account for Bob if they don't already have them. This concludes the overview of the architecture of our program. Let's now take a closer look at the state.rs file. This is our main data structure, an escrow account. Every time we create a new escrow, we're creating one of these. Up top, we use the account macro to let Anchor know that this is a Solana account that will be stored on chain. This automatically gives us certain capabilities for interacting with the structure, such as being able to serialize and deserialize the data. We also derive the init space trait so that Anchor will automatically calculate the size of this account and store that as a constant for later reference. Let's now go over the data inside our escrow. First, we have a seed. The user can send in an identifying seed to make each escrow unique. This lets them put up more than one escrow if they want, even for the same token pair. Next, we have the pub key of the maker. In this case, that's just Alice's pub key. Next, we have the pub key of the token that she wants to give up. In that case, that'll be the Apple coin mint. Next, we have the pub key of the token that she wants to receive, which is the banana coin mint. Next, we have the amount that she wants to receive, which is 20 banana coins. And finally, we have the bump, which is a special number that we use for calculating the PDA, and we'll store it here for easy reference later. One last thing to note is we don't actually track the deposit amount of 10 Apple coins that Alice is putting in. Why is that? Well, that's because the vault is already going to track that, so we don't need to duplicate this data. All right, that sums up the escrow. Pretty straightforward. Let's move on to actually understanding the logic. Let's check out the main logic, which is always in lib.rs for any Anchor program. At the top, use anchor-lang prelude star imports all the typical necessary definitions that we need for this project. Next, we're going to be importing the context module and using all of its definitions in this file. Recall that the context module is made from the mod.rs file inside the context folder. This file grabs the definitions from make, refund, and take into itself and then re-exports them. Next, we're going to be importing the escrow state structure we just reviewed. We also export this state publicly so that any file in this project can use that escrow data structure directly. Finally, for the top, we see this declare ID. This declares the public key of our program on chain. This is automatically generated by Anchor, so we don't need to change it. Let's move on to the body of the file. Here we see our main module, anchor-escrow, which defines the main ways that someone can interact with this program. The use super star line just grabs the definitions that we imported above and brings them inside. Next, we see three functions that correspond to making a new escrow, refunding an escrow, and taking an escrow. Let's quickly pay attention to this context structure that we see passed in as the first argument to all three functions. This is one of Anchor's main conveniences. It packages together all the accounts and metadata that you need to run this function. In the case of make, we derive the accounts from a structure we create called make. That's going to have all the accounts that you need to run this function. So make is going to take this context, a user provided seed, deposit amount, and desired receiving amount. Inside the make function, we simply call two functions which are defined in the make.rs file. Let's pay a little more attention to the syntax here. So when we put this make structure into the context, Anchor is going to automatically put those accounts into this accounts structure here. That's what lets us call this deposit method on those accounts. These accounts are the accounts given in make. The question mark at the end here means that either this function succeeds or it errors out and quits the transaction. Next, let's look at the refund function. It just takes a context which contains this refund struct, which contains all the accounts that you'll need for that. It simply calls one function which is defined in the refund.rs file. The take function is similar. It just takes a context which takes all the accounts that it needs, and it's going to call two functions that are defined in the take.rs file. So to summarize lib.rs, it's some boilerplate at the top and interfaces for our three main functions down below. However, all the logic of those functions is hidden away in the three corresponding files. Let's dig into them. It's time to get into the logic for our three main functions. We're going to go through make the most slowly and carefully, since we'll be learning a lot of new concepts. After that, we can go through refund and take more smoothly, since we'll be reusing many of those concepts. Let's get into the logic for making a new escrow. At the top, we have our standard anchor import, as well as an import from anchor-escrow that brings in a bunch of definitions we use to interact with tokens. Associated token lets us interact with the associated token program to generate wallets that hold particular tokens. We also import a transfer checked function and structure to let us perform a safe token transfer. While transferring, this checks the decimal places of a token so that you don't accidentally send $1,000 instead of $1. We import the account type for a token mint, a token account, and a token interface structure that lets you talk to the token program. That might be a lot to remember, so just remember that these are all tools that we need to work with tokens. You can always look up the individual definitions later. For our final import, we bring in the escrow data structure that we defined in state.rs. Note that this looks different from the import that we used in lib.rs. This is because lib.rs brought in the whole state file and re-exported its definitions, making the escrow struct globally available in this code. We then grab that struct directly here in make. Now let's get into the make struct, which defines all the accounts that we need in order to make a new escrow. A few things to quickly note here. Derive accounts allows us to validate the accounts that we're passing in here. Instruction seed u64 gives the structure access to the seed that Alice passed in when calling make. And this info lifetime specifier, which is the same for all the data here, this just tells the Rust compiler, let's hang on to all this data for the same amount of time. First, we have the maker. The maker, in this case, is just Alice. It's mutable. Her account is mutable because we need to take some lamp ports from her account for rent. She's also going to be the signer of this transaction. Next, we have the mint account for token A. In our case, that'll be the Apple Coin mint. We enforce that it's a mint owned by the token program. Next, we have the mint account for token B. We're also enforcing the same thing. Note that we're actually enforcing that mints A and B belong to the same token program. In Solana, there's currently two token programs, so this escrow wouldn't actually work if these two tokens belong to different token programs. However, this is just for simplicity in this demo example. Next, we have the maker's associated token account for token A. In other words, Alice's Apple Coin account. It's mutable because we need to take some Apple Coins out for the escrow. We also check to make sure that it matches the mint for A, that Alice is the authority, and that it belongs to the token program. Next is the escrow that we're going to create for Alice. The init trait means that we're going to create it right now. The person that's going to pay to create it is going to be Alice, the maker. The amount of space we need is going to be 8 bytes for the anchor discriminator plus the init space that we described for the escrow struct earlier when we made the struct. This is a PDA, so it's going to be generated based on some seeds. The seeds are going to be the word escrow as bytes, Alice's pub key, and whatever seed she provided to identify the escrow. Finally, we're going to store the bump value too. Next, we're going to have the vault account, which is going to hold Alice's 10 Apple Coins for the escrow. We're also going to initiate the account, and Alice is going to pay for the rent. This is an associated token account, so we're going to check that it is for mint A, the Apple Coin mint, that this escrow program is the authority for it, and that it belongs to the same token program as we're using for all these other ones. Finally, these last 3 accounts are just 3 standard accounts that live on chain that we need to interact with. That's going to be the associated token program to create new associated token accounts for people, the token program, which controls all tokens, and the system program, which controls all user wallets. Now that we covered the accounts inside of the make struct, we can understand the functions. This implementation block defines methods on the make account struct, which mutate the accounts inside of it. That's why the first argument to both of these functions inside is a mutable reference to self. The first function, save escrow, is pretty simple. We just pass in the seed that Alice provided and the desired amount that Alice provided, as well as a bump automatically calculated by Anchor. Then we just save all the escrow data. That's the seed, Alice's pub key, the Apple Coin mint, the Banana Coin mint, the desired receiving amount, and the bump. After saving the escrow, we should put Alice's 10 Apple Coins into a vault. That's what deposit does. Note that this escrow program is not the owner of the vault. The vault is a token account, and so it's owned by the token program. The escrow is the authority that can authorize changes to the vault, but it has to ask the token program to do so. Therefore, we need to make a CPI here. We're going to use this transfer checked CPI, which transfers tokens from one account to another with an extra decimal check for safety. First, we're going to create a transfer check struct containing all the accounts we need to make this transfer. That's going to be the source account, which is Alice's Apple Coin account, the token mint, which is the Apple Coin mint, the destination account, which is the vault, and the authority that can authorize the transfer, which is Alice. Next, we're going to use Anchor's CPI context new instruction to pack all these accounts up along with the destination, the target program, which is the token program. This makes everything ready for the CPI to take place. Finally, we actually make the CPI by calling transfer checked with the context we created, the deposit amount, and as an extra safety check, the decimals of the token mint A. All right, so we just finished going through the logic of the make function, and now we're moving on to refund. There are a lot of new concepts, but we'll be seeing them again in this file, so we'll move through a bit more quickly. At the top, once again, we have the standard Anchor import, an import to get some tools for working with tokens, and an import of our escrow data structure. Once again, we're going to create a structure to contain all the accounts that we need to specify a refund. Let's get into them. So if Alice is initiating a refund, she'd be the maker of the refund request. Her account should be mutable because we'll refund some rent to her and she needs to sign the transaction. Next, we need to specify the mint A, the mint of the token that's in the vault, the Apple Coin mint. Next, we should specify the maker's associated token account for token A, or in other words, Alice's Apple Coin account. We need to specify this because we're going to put the vault tokens back to it and it's going to be mutable. We also perform some checks to make sure that it does indeed come from mint A. The authority is Alice and it belongs to the token program. Next, we need to provide the escrow account. We close it out when refunding, so there's a few things we do. We mark it as mutable, and we use this constraint close equals maker to easily close it out and refund the rent back to the maker, Alice. In addition, this has one constraint does an extra check to make sure that we're closing the right account. This makes sure that the escrow has a field called mint A and that it matches the mint A that we're providing here. It also makes sure that the escrow has a field called maker and that it matches the maker we're providing. Finally, since it's a PDA, we need to provide the seeds and bump to look it up. We also need the vault. Since we're closing it, we mark it as mutable. However, since the token program owns the vault and not this escrow, we can't use the close constraint like we did with escrow. So we'll close it with a CPI, just like we did in make. We need to use a CPI to deal with the vault. Since we're going to send this vault along in the CPI, we mark it as public. Finally, these last three accounts are just standard programs that we're going to be interacting with. That sums up all the accounts needed for a refund. Let's now understand the implementation. There's only one function, refund and close vault, and it does what it says. It calls two CPIs, one which refunds the vault deposit to Alice and the other which closes the vault. To refund the deposit, we start by creating this structure called signer seeds. These are the seeds that serve as a signature of the escrow PDA to prove it has authority to close the vault. Recall that PDAs don't have private keys like user accounts, so they use their seeds instead. This structure looks kind of weird, so let's dive into it. Each and brackets U8 is a byte slice, which represents a single seed, a single piece of text. We have a slice of those, which represents all of the seeds for a single PDA. Then we have a slice of those, which represents there may be more than one PDA signing. However, in our case, we specify that there's just one PDA signing. In the structure, we're going to put in the same seeds that we use to make the PDA. Next, we're going to follow the same protocol to perform a CPI that we learned before. First, we create a structure containing all the accounts that we're going to touch. So we're going to say that the transfer is going to come from the vault. Next, we're going to say that the mint of the token is going to be the Apple Coin mint. Next, we're going to say that the target is Alice's Apple Coin account. Finally, the authority is going to be Alice's escrow. We package all those accounts up into a CPI context along with the target program and the seeds, and then we perform the transfer CPI. Once that's finished, the last thing we need to do is perform the CPI to close the vault. Once again, we make an account structure. We say that the account we want to close is going to be the vault. We specify a destination, which is where the rent goes after we close the account, and it goes back to Alice, the maker. Finally, the authority is the escrow, Alice's escrow. Once again, we create a CPI context to package all that up with the seeds, the signer seeds, and the target program, and then we perform the CPI. That concludes our analysis of the refund logic. We're now on to our last function, taking the escrow. At the top, we have our standard 3 imports. Once again, we're going to create a struct which lists out all the accounts that we're going to need to use. This time, Bob, the escrow taker, is the one who initiates the transaction, not Alice. His account is mutable because he'll pay some fees, and he signs a transaction. We also list the maker, Alice, and mark her account as mutable only because she's going to get some rent back when the escrow is closed. We provide the mints for tokens A and B. Next, we provide taker's account for token A. In other words, Bob's account to store Apple coins he will receive. This account may not exist yet, so we use the constraint init if needed to create it if it doesn't exist. We specify that Bob will pay the fees to create the account, and we also perform some checks to make sure that this is the right account. A technical detail here. You may know that Rust has 2 memory locations, the stack and the heap. We use box to specify that this account should be on the heap because init if needed might use a variable amount of memory. Accounts are otherwise kept on the stack. Next, we have taker's account for token B, or Bob's banana coin account. It's mutable because we're going to take some of his banana coins for the swap. We also perform some standard checks. Next, we have maker's account for token B. In other words, Alice's account to receive banana coins. We're going to create this account for Alice if it doesn't exist, and the taker, or Bob, is going to pay for it. This is because Bob is the one who needs the transaction to go through, and we aren't going to wait around for Alice to sign. We also do some standard checks. We're passing in the escrow. The escrow is going to be mutable because we're closing it, and we're going to use this close equals maker to close it out and send the funds back to Alice, the maker. We're also doing this has one check for maker, mint A, and mint B to make sure that this is indeed the right escrow that was made by Alice and is for the Apple coin and the banana coin. We're also going to list the vault and list it as mutable because we're going to be closing it out. Finally, we have the 3 standard programs that we're calling: the associated token program, the token program, and the system program. Now let's dive into the functions defined on the take struct. There's 2 functions, deposit and withdraw and close vault. The deposit function is a simple transfer checked CPI, a pattern we already saw twice now. We deposit Bob's banana coins from his banana coin account to Alice's banana coin account, and Bob authorizes it. For the 3 steps, we create the account struct, we create the context, and then we send the transaction. Next, the withdraw and close vault function takes Alice's 10 Apple coins out of the vault, gives them to the taker, Bob, and closes the vault. The logic of this function is almost exactly the same as refund and close vault from the refund file that we just reviewed. The only difference is that we send the funds to Bob rather than Alice. So we create the signer seeds for the escrow PDA, then we follow the 3 steps to perform a CPI. We gather the accounts, we create the context, and then we send the transaction. We repeat this process for the close account instruction. We gather the accounts, we create the context, and then we send the instruction to close the vault. That's it. Now we finish studying the logic for the entire escrow program. I hope you enjoyed learning this escrow program together with me. For next steps, feel free to grab the code from the GitHub repo and run anchor build and anchor test in order to deploy it on DevNet or your local machine and run some tests to see it in action. I hope this tutorial is the start of some awesome projects to come. Happy learning and see you around.